Hey folks, how's it going? In this video we're going to go over 3 worked examples to show you how to do problems involving absorption spectra. Now if you haven't already done so, check out my previous video covering the theory on this topic, and that way you can apply what you learned in that video to this one. So let's get going. Question 1 says the diagram represents some of the energy levels for an atom of gas. So we have energy levels E0, E1, E2 and E3 with their energy values at the side. And it says white light passes through the gas and absorption lines are observed in the spectrum. Which electron transition produces the absorption line corresponding to the longest wavelength? Justify your answer. Well, remember longest wavelength means the lowest frequency, since wavelength and frequency are inversely proportional. And then we know that the lowest frequency means the smallest change in energy from the relationship delta E equals HF. So remember delta E is directly proportional to F, and therefore the lowest frequency means the smallest change in energy or energy difference. So because we're thinking about absorption spectra here, we're not thinking about electrons moving down the way and transitions down the way, we're thinking about electrons moving up the way because these atoms are absorbing photons, remember, and that is causing electrons to be excited. So the smallest energy difference here is going to be the smallest gap between two energy levels, which is going to be from E2 up to E3. So our electron would be excited from E2 up to E3. So we can write E2 to E3 with an arrow, or you can write the word 2 instead. Question 2 says the following diagram shows some of the energy levels for a particular atom. So we have E0, E1, E2 and E3 all with their energy values. And it says an electron is excited from energy level E2 to E3 by absorbing light energy. What frequency of light is used to excite this electron? Well, first we want to find the energy difference between the two energy levels. So we're trying to find the change in energy delta E. We know that E3 is equal to minus 5.2 times 10 to the minus 19 joules from the picture here. And E2 is equal to minus 9.0 times 10 to the minus 19 joules, also from the picture. So writing down our expression for the energy change, we have delta E equals E3 minus E2. Substituting in the numbers gives minus 5.2 times 10 to the minus 19 minus 9.0 times 10 to the minus 19. And remember the double negative here will become a positive, so we're essentially doing this value plus 9.0 times 10 to the minus 19 joules, which will give us a positive energy difference, and putting that into your calculator should give you an answer of 3.8 times 10 to the minus 19 joules. Now it's worth pointing out here that even though our transitions this time are going up the way instead of down the way, which was the case for emission spectra, we still do the upper energy level take away the lower energy level, as is the case here, because otherwise we wouldn't get a positive energy difference, and that's what we want. So now we can calculate the frequency. So we're trying to find F. We note the energy difference delta E is 3.8 times 10 to the minus 19 joules. Planck's constant H is 6.63 times 10 to the minus 34 joule seconds. So writing down our equation relating delta E and F, we have delta E equals HF. Substituting in the numbers gives 3.8 times 10 to the minus 19 equals 6.63 times 10 to the minus 34 times F. And to find F on its own, we need to divide both sides by this 6.63 times 10 to the minus 34. So doing that in your calculator, you should get an answer of F equals 5.73 times 10 to the 14 hertz. Lastly, question 3 says the sun emits a continuous spectrum of visible light. When this light passes through hydrogen atoms in the sun's outer atmosphere, certain wavelengths are absorbed. Part A says, what do absorption lines in the sun's spectrum provide evidence for? Well, remember from the theory video on absorption spectra, the absorption lines in the sun spectrum provide evidence for the composition of the sun's outer atmosphere. In other words, it just tells us what the sun's outer atmosphere is made up of. Part B then says the diagram below shows some of the energy levels for the hydrogen atom. So we have energy levels E0 up to E3, and the energy value is shown here. And it says one of the wavelengths absorbed by the hydrogen atoms results in an electron transition from energy level E1 to E3. So that would be from here up to here. And it says calculate this wavelength. Well, we first need to find the energy difference between the two energy levels. So we're trying to find delta E. We know that E3 is minus 1.360 times 10 to the minus 19 joules. And we know that E1 is minus 5.424 times 10 to the minus 19 joules from the picture before. And writing down our expression for the energy change, we have delta E equals E3 minus E1. Substituting in our numbers gives minus 1.360 times 10 to the minus 19 minus 5.424 times 10 to the minus 19, and putting that into your calculator should give you an answer of 4.064 times 10 to the minus 19 joules. And now we can calculate the wavelength. So we're trying to find lambda. We know that delta E is 4.064 times 10 to the minus 19 joules. Planck's constant H is 6.63 times 10 to the minus 34 joule seconds, and the speed of light c is 3 times 10 to the 8 meters per second. Remember, these last two values are on your datasheet. So writing down our equation relating delta E and lambda, we have delta E equals HF equals HC over lambda, where remember this is the shortcut method combining two equations together, the delta E equals HF and V equals F lambda, the wave equation. So we're just replacing the frequency F with C over lambda, where C is our speed V. And substituting in our numbers, we get 4.064 times 10 to the minus 19 equals 6.63 times 10 to the minus 34 times 3 times 10 to the 8 divided by lambda. And then to get lambda on its own, we need to swap these two terms. So we would get lambda equals the numerator here divided by this 4.064 times 10 to the minus 19. So doing that in your calculator should give you an answer of lambda equals 4.89 times 10 to the minus 7 meters, or in other words, 489 nanometers. Part C says the absorption of this wavelength produces a faint dark line in the continuous spectrum from the sun. In which colour of the spectrum is this dark line observed? Well, here you would want to check your datasheet, and we can say that from the datasheet, 489 nanometers for hydrogen corresponds with the blue-green, which is 486 nanometers. So because it's very close, we could say the colour of this light is blue-green. But note that you could also get away with stating just blue here. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video one of these, subscribe to the channel, and I'll see you in the next one. Take care.